So what I intend to do today is, what I explained last time is that, one can compute formally the trace of the action of a flow on functions of the manifold. Okay, and the formula that we got was the following type. So it was a sum over all periodic orbits, but including the fixed points. So over all periodic orbits of integrals. So the integral was performed over the isotropy, independent of the point that you take on the periodic orbit. And then the test function h was evaluated at a point u, and or t if you want. And then there was 1 minus the Poincare return map. Absolute value means the determinant, and dt, where dt is the R measure on R. Okay, and obviously this formula was proved in such a way that it's not specific to flows. It could be extended to certain class of groups and so on. Okay. Now, the key observation, on which most of what I am talking about is based, is the following observation, that when you compute the similar formula for the action of the ideal class group Ck acting on the space X of Adel classes, namely the quotient of A by GL1 of K, okay, then you obtain a corresponding formula. I will explain it much later in detail. So for the time, I just tell you what the formula is. And the formula that you obtain for the trace is the following. It turns out to be the sum over all places. So V is a place of the global field K. And then you have, for each place, you have the integral over the local field K star, the invertible elements in the local field completed at the place V, of the following expression. So you take the test function h, but because because I was defining the transformation by, for instance, the regular representation was, if you remember, V of u applied to psi at x was psi, not of ux, but of u inverse x. Then the test function has to be replaced by h of u inverse, not h of u. So you get h of u inverse divided by absolute of 1 minus u, and then times d star u. Okay? So you obtain such a sum. Now, it will be absolutely crucial for what I want to do, that this sum, in fact, is known. It already appears, and from the work of André Weil and Riemann, this is the explicit formula of André Weil and Riemann, it is in fact equal to the following. It is equal to the Fourier transform of h at 0 plus the Fourier transform of h at 1 minus the sum of the Fourier transform of h at a Grossen character chi and 0 rho of the corresponding L function. So where L of chi rho has to be 0, and where you can put in the multiplicity of the 0, which I will denote by n of chi and rho. So the sum is extended over all Grossen characters and all zeros of L functions. And what is h hat? Let me explain what is the Fourier transform. So by definition, the Fourier transform h hat of a Grossen character and the complex number z is given by the integral of h of u times the Grossen character chi of u times the multiplicative R measure d star u. U to the z. Absolute of u to the z. Times d star u. So in all this, you have to normalize the R measures very carefully. So here this is the R measure on Ck. It is a multiplicative R measure on Ck. Whereas here you have a multiplicative R measure on d star u. So it's clear if you multiply both of them by 2, nothing changes. Okay? But the only rule is that the covolume of this R measure. So the covolume, so this is the rule in the Weil formula, that the covolume of K star V, if you want, or the covolume of D star U with respect to K star V, okay, is equal to 1 with respect to the R measure D star U and Ck. This is equal to 1. Okay, I will come back to that. Okay, now what I want to do, you see, I mean, one could give relatively simple proof. I mean, in fact, there is this paper you are talking about. Sorry? Why not covolume? I know what I mean by covolume is the volume of the quotient, okay? When I talk about the covolume of the isotropy subgroup, I mean the volume of the quotient, okay? So if you take the quotient measure, the quotient is compact, okay, and you want to prove that the total mass of this quotient is equal to 1, okay? Okay, so I mean, for the time, you see, for the time, what I will sort of talk about and what I talked about in the last lecture, you see, we couldn't treat the transversality at 1, so we have to assume that h of 1 is equal to 0. Okay? We have to assume that h of 1 is equal to 0. Now, we shall remove this assumption later, but this will be much more difficult. Okay, so for the time, I will assume that the test function h vanishes at 0, okay, so that I don't have this problem with the transversality. Namely, that the fact that the identity map is not transversal to the diagonal. Okay? Now, so what I will do, you see, I will start, because it is so important that this formula is correct, and that all signs are correct, and that I get exactly the correct signs when I do the computation, and that I get exactly the correct normalizations, and so on and so forth. Okay, I mean, this is, because if anything would go wrong, the approach would be dead. Okay, I mean, if there was a factor of 2 anywhere, or whatever, or a sign which gets wrong, and so on, the whole approach would be dead. Okay, so I mean, what I want to do is to take an extremely pedestrian, I mean, there are slightly better approaches, like this paper, about proving this formula, but I want to take the most simple approach. I want to take the approach as it was done in Riemann and then Weil, so that we can check all the constants and we can see them with bare eye, okay? So it doesn't depend on something, okay, anything fancy. So what I want to do really today is to give you an account for this proof, for these explicit formulas, and then an account for proving that actually when we do the computation, we do get exactly this expression, okay? And also, remember that what we have seen before. What we have seen before is that, in fact, this trace can be computed spectrally, at least formally, okay? And I will show you that when you compute it formally, spectrally, you do get h out of 0 plus h out of 1, and minus, and of course this minus is coming from the fact that we had a minus sign when we were subtracting the space L2 of x, minus the sum of the Fourier transform. But now, of course, there was this restriction that the real part of rho was equal to 1/2, and there was a restriction about multiplicity. And I mean, this is, if you want, the motivation for the work, but of course much more work requires to be done, and I will do it in part, precisely because then we shall have to make rigorous sense of the trace formula, okay? I mean, this is just the essence of it, or if you want, the distributional part of it, okay? Okay, so what I want to do today really is to give you a completely pedestrian approach of this formula of André Weil, and later, what we shall see is that when we compute by justifying the trace formula, okay, for instance, for finite in many places, we shall get a preferred finite value in this expression, removing the condition h of 1 equals 0, and that preferred value will be imposed on us by the trace formula. It will not be anything artificial, if you want. It will be forced upon us by the trace formula, okay, and it will be, in fact, what one calls a renormalization point in physics. And it will be the fact that a certain Fourier transform of a distribution will be vanishing at the point 1, okay? But I mean, it will be crucial then that we not only recuperate the formula for h of 1 equals 0, which is relatively simple, but that we recuperate the formula in general, and that we do have a completely different approach to prove this formula from the geometric realization, okay? All right, so I mean, this is just preparation. So I mean, as a preparation, just to test, if you want to be sure that all the coefficients and so on are all right, I'm not trying to find a simple proof of that. I am just giving you the most sort of down-to-earth approach, okay? Okay, so let's do it for the, so let's first do it for the Riemann zeta function. Okay, so let me just talk about these explicit formulas. And let's first do it. So let me explain what André Weil did, because I mean, it's really André Weil who put these formulas in a nice way. I mean, when you look at books, and I mean, even book by Patterson or several books, I mean, these formulas look terrible, okay? And I mean, it's only because you Weil put them on the ideal class group, and this is group CK, that they look much better, and that they have this form. Okay? So let me explain how it goes. So let us start with the Riemann zeta function. So you know the Riemann zeta function, if you multiply it by a certain function g of s, which I will call gr of s, and which is equal to pi to the minus s over 2 gamma of s over 2, okay, then it satisfies the functional equation, so that, well, let me denote it by xi of s. I mean, this is not quite happy notation, but doesn't matter. And then it satisfies xi of 1 minus s is equal to xi of s. And this means that in particular what you can do is you can consider the logarithmic derivative, xi prime of s over xi of s. And that, if I multiply it by ds, okay, that differential form is invariant under s goes to 1 minus s. Okay? Okay? I mean, because if you take psi prime of 1 minus s over psi of 1 minus s, there is a minus sign. Okay, but because I put ds here as the differential form on C, it is invariant under s goes to 1 minus s. Okay? Okay, and moreover, if we look at it for real of s, say, bigger than 1, okay, we can, because it's a logarithmic derivative of the Euler product, we can expand it as a sum. And so this means if you want that xi prime of s over xi of s can be written as a sum. In fact, it's a sum over all places if you want, and of certain factors which I could denote by rho v of s. So v is associated either to a prime number or to v equals infinity. Okay, and this rho v can be computed very easily. And now, so what do you do? Of course, what you do is you take the Cauchy integral around a rectangle like this, okay, which you sort of go around in the positive direction. And so let me be very careful in notations. So, I mean, I will just keep the notations of that which are used here, but I mean, I want to be sort of extra careful. So the notation is, let us call the function we are talking about, it will be, let me write it here, perhaps. Yeah, so I want to consider a function f of u, where u is an element of r plus star. Okay, and the function f has suitable properties. For instance, it has compact support. Okay, smooth with compact support on r plus star. And then I want to define another function, which is psi of z equals integral over r plus star of f of u u to the 1/2 minus z times d star u, where d star u is the standard normalized R measure on r plus star, which is just du over u. Okay? Now I forgot to say one thing, which is that the standard notation that will be used always is that when I have a group like the ideal class group or like the local invertible elements in a local field, the normalization of the R measure will be always the same. It will be always such that if I look at the integral over the set of elements so that the absolute value of x belongs to the interval 1 lambda, okay, and if I look at the integral of d star x, that measure, that should be equivalent to log lambda when lambda goes to infinity. Okay, you cannot say that it's equal to log lambda because you see, if you take, for instance, a discretely modulated group, I mean, there will be jumps, so it won't be equal, but it will be equivalent to log lambda. Okay, there will be a term which is of 1. Okay, and now if you take this normalization, which is a standard normalization, what happens is that, of course, if you take r plus star, the measure is du over u by definition of the log. Okay, but if you take, for instance, discretely modulated, like periodic numbers, or like something where the module is q to the power z, where q is a prime power, then what you find out is that the integral on the elements which have norm 1 for integral of x equals 1 of d star x has to be equal to log q. And the reason is quite simple. The reason is that when you look at the integral, between 1 and lambda, if lambda is a power of q, you will get n times the integral here. But that has to be equal to log of q to the n. So, I mean, that has to be equal to log q. Okay? So, I mean, this is how the log of the Q is introduced by this normalization. Now remark another thing, which is that if you normalize the R measure, the multiplicative R measure in that way for the ideal class group, okay, which is the group CK, and if you normalize it in that way for the subgroup which is given by the multiplicative group K star V, okay, then it is automatic that the covolume is equal to 1. All right? So I mean, all of these things are quite important. You see, I mean, this normalization is sort of hereditary. If you normalize in the same way the R measure on the subgroup, on the closed subgroup, then the covolume has to be 1. For that, you just compute in two different ways this integral. Okay? Either you compute it upstairs, or you compute it by Fubini. Okay? And you get 1, obviously. Okay, so you have this normalization. Okay, so now, so what do you do? I mean, so you compute this integral of what? So you compute the integral over this curve, if you want, this rectangle, let me say, R, of the product of psi of S times psi prime of S over psi of S ds. Okay, that's what you do. Okay? And to compute this integral, well, I mean, I'm not interested in standard details, but what you find out is that the integral on that part is actually negligible when the size of the rectangle goes to infinity. So in fact, what you really have to do is to write down the sum of the integral on this vertical line plus the sum of the integral on this vertical line. Okay? And what do you get? Well, what you get is clear. If you want, if we divide by 2I pi, okay, what you will get are the, because you do it in the positive orientation, so certainly you will get the sum of the multiplicities of the zeros, where when I talk about the multiplicity of a 0 for psi, I mean that the multiplicity is positive. For instance, if you take a 0 of order 1, the multiplicity is 1. Okay? So, and you'll get also minus the value of psi at the pole. So the pole, there is a pole at 1 and there is a pole at 0. Okay? Minus psi of 0. So that's sort of clear just from the Cauchy formula in the limit. Okay? And moreover, you can now write this, as I said, you know, as a sum, as the integral here and the integral there. Now, the first integral, what does it give you? Okay, so it gives you 1 over 2I pi integral, say, from minus infinity to infinity. And then you can exchange the summation and the integral. So in fact, it's, if you want, it's a sum over places. And each time now you have to take in account this term rho v of s multiplied by, okay, so rho v of s, if you want, multiplied by psi of s ds. Okay? As I said, you know, I want to do it in the most pragmatic. I mean, the method is, let me just make a little joke, you know, because I don't know, I can't resist to make this little joke. Okay? So the joke is about a dog which is called Cauchy, you know. And when you apply the Cauchy formula, I mean, you sort of walk this dog, and it leaves a residue at each pole. Okay? That's pretty bad. Okay, and I mean, this is a standard method that you use to prove this formula, okay, this explicit formula. Okay, so anyway, I mean, now we have to consider this term here. Okay, and we have to consider it individually for each place V and understand what we get. Okay, so what I want to watch out for are the signs and the normalizations. Okay, I really want to watch for everything like that. Fine, so let's first take a finite place. So for a finite place, what is rho V of S? Okay, so I mean for a prime P, say. So what is rho P of S? Rho P of S is obtained by applying the Euler product formula. So it's coming, if you want, in the logarithmic derivative from the logarithmic derivative of 1 minus, I mean, so the derivative of this, 1 minus P to the minus S inverse, so it's coming from this. Okay? I just want to show you that the minus sign is the same as the one I was talking about in the first days. Okay, so when you take the logarithmic derivative of that, okay, that is the derivative of this quantity, what do you get? Well, because of the p to the minus s here, you get a log p. Okay? Now, there are three minus signs. Okay? There is this overall minus sign, there is this one here, and there is that one here. So it gives you an overall minus sign. Okay? So it gives you an overall minus sign. And what you get is like p to the minus s divided by 1 minus p to the minus s. Okay? But it's sort of better to expand this in powers. Okay? So in other words, what it gives you is that this is equal to minus log p times the sum from m equals 1 to infinity of p to the power minus ms. Okay? But observe that I didn't put 0 here. Okay? And observe that this quantity is positive and I put a minus sign in front. Okay? Now what can we say when we invert this formula? Okay, what we can say is that we have, of course, the Fourier inversion formula. And the Fourier inversion formula tells us that the following holds. If you take 1 over 2i pi, the integral from minus I infinity to I infinity. I suppose this is clear what I mean by this. Okay, of psi of z times lambda to the z dz. Okay, because I am taking from minus I infinity to plus I infinity, there will be an I which drops out. Okay, and moreover, the 1 over 2 pi is from the Plancherel formula for the real line, if you want, so it will drop out. And what you get there is equal to, so I shouldn't make a mistake. You see that in this formula there is f of u1/2 as a block. So in fact, you cannot separate these two things. I mean, there will always, when f will appear, there will also be u to the 1/2. Okay, so I mean, it's sort of clear that you get here f of lambda times lambda to the 1/2. Okay? Because I put a minus in the z here. Okay, so the two terms cancel. I mean, this is just the formula for the Dirac mass at the origin. Okay? I mean, this is just a Fourier inversion formula. Fine, so you have this formula. So now you see what this term here will give you for a prime. So what will it give you? So we have the 2i pi, okay, and we have this integral from minus, I mean, this is from minus I infinity to I infinity because I'm going upwards. Okay, and what do we get? So we get a log p, certainly, and we get a sum from m equals 1 to infinity of terms. Okay, so as I said, I mean, I am doing it extremely slowly. So what we get is log p times the sum from m equals 1 to infinity of what? Well, you see that you have 1 over 2i pi times the integral here of psi of s, exactly as we have over there. And then we have a lambda to the z. But what is lambda? It is p to the minus m. Okay? So what we get is certainly f of p to the minus m, f of p to the minus m, and then p to the minus m over 2. Okay? But there is an overall minus. Okay? Because of what I had here. Okay? So we see that it is something which is negative. If the function f is positive, we get a negative answer. All right? Now, this is what we get by doing the integration over this part of the contour. Now, when you do the integration over that part of the contour, it's very easy to do it because we know that the differential form, which is given by xi prime of s over xi of s ds, is invariant under changing s to 1 minus s. Okay? So in fact, when you change s to 1 minus s, you transform this line into that line here with the correct orientation. Okay? Which means what? Which means that the only thing that you have to do is to change psi of s into psi of 1 minus s. Or rather, sorry, you have to change rho of s into rho of 1 minus s. This is the best way. Okay? Because the differential form which is here, sorry, am I correct or not? No, I am not. No, sorry. So, no, what you have to do is to change psi of s into psi of 1 minus s. That's what you have to do. Okay? In each term now, you can do it in each term. You first do it globally, of course, nothing changes, and then you do it in each term. So here I will have to replace s by 1 minus s, okay? And what will it change? Well, what it changes simply is that instead of having the sum with f of p to the minus m, p to the minus m over 2 here, what you will get is another sum with the same minus sign, and it will be the sum, if you want, of f, this time of p to the plus m, but it will still be with p to the minus m over 2. Okay, so in other words, it will be p to the minus, yeah, okay, so let me just write it like this, okay? So this is from m equals 1 to infinity. Now, of course, there is a nice way to put these two terms together, which is minus log p times the sum for m belonging to z, but m different from 0, okay, m not equal to 0, of f of p to the m, f of p to the m, and then p to the minus absolute of m over 2. Okay, which is the usual way it's written. Okay? Okay, so this is what you get from this term. And fine. All right. Okay, so let's look at it a little bit, and let's rewrite it a little bit better, this. Okay, so we can rewrite this a little bit better, because, you see, I told you that the log p, we know where it comes from. The log p comes from the normalization of the R measure in the local field now, which is periodic numbers. Okay? So, so what I want to tell you simply is that it is the same, this formula, as the following thing. Okay, so I mean, for all primes, we have something which is fairly obvious. Okay? Now, so I want to rewrite this as follows. You see, now this is the contribution I get, okay, for each prime. Now I want to rewrite this as minus the integral over periodic numbers, 2p, non-zero periodic numbers, okay, of what? Of f of absolute value of u times u to the 1/2, okay, divided by, okay, times d star u, divided by absolute value of 1 minus u. Okay? And for that, I will assume for simplicity that f of 1 is equal to 0. Okay? But I mean, otherwise, it's very easy because you just put 0 here. Let me assume that f of 1 is equal to 0. This doesn't matter for this discussion. Okay? So if I assume that f of 1 is equal to 0, I have no contribution in this integral here of the place where the norm is equal to 1, okay, by assumption. Okay, that's clear. Now, what do you get here? You get an integral over periodic numbers which are of norm strictly less than 1, and an integral over periodic numbers which are whose norm is strictly bigger than 1. Okay? When the norm of u is strictly less than 1, this is equal to 1 because of the properties of the norm. Okay? Moreover, it will be a sum which only depends upon the absolute value now. Okay? And the absolute value will be just equal to p to the minus m over 2. All right? But then you have to know what is the integral on the corresponding set of elements which have a given absolute value. But that doesn't change because this is a multiplicative R measure. And it's always equal to log p. Okay? Now, if you take elements u which have norm bigger than 1, when they have norm bigger than 1, the norm of 1 minus u is the norm of u. So in fact, you pick a factor of norm of u to the power minus 1/2. Okay? And this is the first beauty of what is the Veil formula. Of course, for that, this is very, very simple. But we shall see that for ramification, the whole interesting stuff will occur for when the norm of u is equal to 1. Okay? But for the Riemann zeta functions, this doesn't occur because the Rosen character is never ramified. It's just the identity. Okay? So we are fine, and we have rewritten it in a sort of nice way. Okay? But of course, preceded by a minus sign. Okay? I suppose this is very clear. Okay, so let me perhaps put it over there, what I want to keep. So what I want to keep is that the contribution of this local thing for a finite place, it's a sum, first over p, say, of the integral over qp star of f of u, absolute of u, sorry, u 1/2 over 1 minus u d star u. And observe that it was crucial here, that's one place where we can see things with bare eyes, that the R measure of the subgroup had covolume 1. Okay? It was crucial because it was precisely at this point that the log p were appearing. Okay? I mean, the only keyword today is being careful. All right? I mean, I don't want to make a short proof or anything. I want to be hyper careful. And in fact, all the details of the proof will be used later. Fine. Now let's look at the infinite place. So the infinite place, for the infinite place, the local term, if you want, rho infinity of s. Okay, rho infinity of s, what is it? It is given by the logarithmic derivative of the function pi minus s over 2 gamma of s over 2. So what is that? I mean, this is equal to minus s over 2 times log pi. Oh, sorry. I'm crazy. It's minus 1/2 of log pi. Okay, because this was just a log. Okay, and I take the derivative. So it's minus 1/2 of log pi. And then I have another term, which is plus 1/2 of gamma prime of s over 2 over gamma of s over 2. Okay, so I sort of need a nice formula for this, because you know the essence of what was being done was to write down these local terms in a nice way. You see, what was nice about this writing up of rho p of s was that we were writing it as a Laplace transform. You see, it was a Laplace transform because it was a sum of such powers. That's exactly what is called a Laplace transform. And once it was in the Laplace transform, we could use this formula to replace by its value. So in fact, we have to write gamma prime of s over 2 over gamma of s over 2 as a Laplace transform. So let's do that. I mean, you know, this is just child play. We should do it. So let me remind you. Okay, we are just easy going. So let me remind you of a standard formula on the functions. So the standard formula is the following: that you have that 1 over gamma of s is equal to s times exponential of cs, where c is the Euler constant, times the product of 1 plus s over n multiplied by e to the minus s over n. Okay? So the product is from n equals 1 to infinity. Now, if you use this formula, I mean, what you find out is that the Euler constant plus the logarithmic derivative plus gamma prime of s over gamma of s, I mean, it's clear that this is a correct combination somehow. Okay? This is the correct combination of the two. Okay? So, I mean, this sum here is equal to the integral from 0 to 1 of 1 minus x to the s minus 1. So let me prove it. Over 1 minus x dx. You see, I mean, it's sort of obvious because I just expand 1 over 1 minus x as a sum of xn. Okay? And of course, then when you integrate, there is a s, so you'll pick up exactly the right factors. Okay? So, I mean, this is clear. Okay, so what does it mean now? It means that, but this will be useful later. So this means in particular that when we look at this quantity here, rho infinity of s, okay, we can write it as rho infinity of s. So now it's written as a Laplace transform, really. Okay, because it's an integral and I have powers of x. Okay, and this integral makes sense even at 0 because I made sure, you know, that. Okay, so now rho infinity of s is equal to minus 1/2 of log pi. Okay, then I want to use this integral. So I want to put minus c over 2. I mean, all these terms will be crucial later. Okay, all these finite values will be very, very important. I mean, it was very important that eventually they will all get explained by a very simple formula. I mean, that's certainly quite important. I mean, which comes from the trace formula. Now, so minus c over 2. I have just erased what I needed. That's okay. Requires a little bit of thought. Okay, and then normally I would write plus 1/2 of integral from 0 to 1 of 1 minus x, and then I would have to put s over 2 minus 1, okay, over 1 minus x dx. But it's clear here that I should change variables. I should put x equals y squared, okay? Because if I put x equals y squared, I will get rid of the 1/2, and I will get rid of the 1/2 power here. So what you can see very easily is that this is in fact equal to the integral from 0 to 1 of y squared minus y to the s over 1 minus y squared multiplied by d star y, okay, by dy over y, if you want. Okay, I suppose this is obvious. You see, I mean, it's a little bit clumsy, but I have a y square here and a y here, so they give me exactly what I need for d of y square, okay, which is y dy. So, fine. All right, so now we can use this formula. These terms, let me put them on the side, because they will just affect h of 1. Okay, and they will be taken care of later. What is very important is that they are there, but they are fixed. Later on, we shall see how to explain them. Not only how to explain them for the explicit formulas, this is irrelevant, but how they come from the trace formula. Okay, like Zellberg trace formula. Okay, so now let me check the following fact, which is that in fact rho infinity of s. Okay, so rho infinity of s. So let me just transport it here. Is up to a constant. Okay. So what is it up to a constant? I mean, what is the relevant term? The relevant term is this minus ys. And the others are sort of constant. Okay. So it's like, if you want, integral minus integral ys over 1 minus y square. Okay. dy over y from 0 to 1, okay, plus constant. I am slopey because this integral is divergent at 1. But that's why I put plus constant. I mean, up to something which is independent of s, this is correct. Okay, the constant you can reinsert in the formula if you want, but I don't care. Okay, I mean, this constant is minus 1/2 of log pi minus c over 2. And then I have to put the 1 here. But I don't care. For what I'm doing, it doesn't matter. Okay, why? Because now what do? We take the integral of phi of s, sorry. So we take 1 over 2i pi, integral of phi of s, rho infinity of s, ds. Okay, I will write the constant term eventually. It doesn't matter. And I mean, this is equal by what we know, namely by this inversion formula over there. It's equal to minus the integral from 0 to 1. Okay, of what? Of, now we have ys, okay, multiplied by phi of s. But we know what this is. This is given by this Laplace inverse transform. So what we shall get is minus f of y, okay, y to the 1/2, okay, just because I have the ys here. Okay, and then we have what? We have 1 over 1 minus y square, okay, and then we have dy over y, all right? Plus constant. But the constant is not there because f of 1 is 0. Is that clear? Okay, if f of 1 is 0, there is no constant. Okay, if you want plus constant times f of 1. But this is just to get rid of f of 1. All right? I mean, you see, if f of 1 is 0, that integral makes sense. It converges even at for y equals 1. All right? So that's why I don't care for that. I'll come in later. Okay, so this doesn't look very nice. Doesn't look very nice, but somehow, I mean, again, what André Weil observed is that this is equal, in fact, to the integral now over r star. That's the beauty somehow. Okay, now you take r star, not r plus star. Okay, and you endow r star with a measure which is not du over u, but which is 1/2 of du over u. Because it's only for that measure that this condition is true. Okay? So R star is not endowed with a measure du over u. R star is endowed with a measure 1/2 of du over u. Okay? I suppose this is clear, what I mean by this. Du over absolute of u. Okay? Now, so this is equal to integral over R star of what? Of f of absolute of u, okay, multiplied by u to the 1/2 again, and multiplied by 1 over absolute of 1 minus u, and this star u. Okay? But it's not equal to integral over r star, it's integral with the condition that absolute of u is less than 1. Okay? Okay? So let me tell you why. Well, it's sort of obvious. This function is even function. So when you integrate it, you can just integrate where u is positive and where u is negative. What you will get? You will get 1 over 1 minus u. Okay, this is for positive u, plus 1 over 1 plus u. Okay? But you have an overall 1/2 because the measure is multiplied by 1/2. Okay? And this is equal to 1 over 1 minus u squared. Okay, which is just what we have there. All right? So, I mean, you can see in that case already, I mean, all of this was found by André Weil. I mean, so you can see that there is some pattern going on. And that pattern is that, in fact, you see the contribution we are talking about, which is the contribution of the upgoing vertical line, can be rewritten in a much better way. It can be rewritten as minus the integral over r, but for absolute of u less than 1, of what I wrote here, namely f of u, okay, which is absolute of u to the 1/2, multiplied by 1 over absolute of 1 minus u, and again with the assumption that f of 1 is 0. Okay? Now what about the other integral? What about the integral when you go down this line? As I said before, the only thing you have to do is to replace psi of z by psi of 1 minus z. Okay? So in fact, what do you have to do? It's very easy to see that you get the same integral, but now with absolute of u bigger than 1. All right? And in fact, of exactly the same quantity. Because in fact, you see, when I write integral of, let me write it in the old way, and then you will see what happens. So you can write it like this, f of u inverse. This is what you would get if you would be just doing it naively. Okay, this is what you would get. 1 minus u. P, 1 minus u inverse, I think. Yes, this star u. This is what you would get. You would get a u inverse here. Because you would get a u to the plus 1/2. Okay?
That is for the left arc.
That's for the left arc, okay? I mean, what you get normally is a u to the plus 1/2 here and no minus 1 here. But that's, of course, the same thing as u to the minus 1/2, 1 over 1 minus u inverse. Okay, because the absolute value of 1 minus u inverse is, okay, cancels out. All right, but you see what this is? I mean, this is, of course, the integral for absolute of u bigger or equal to 1 of f of u, f of absolute of u, multiplied by u to the 1/2, d star u over 1 minus u. Okay? Sorry? With a negative sign. So if you add the two terms, what you find is extremely simple. And it is exactly the same as here, namely it is minus it's not a sum now, it's just the integral over r of f of u to the 1/2 over 1 minus u d star u. Okay, and all of this assuming f of 1 is equal to 0. All right? Fine. So you see that there is a very general and nice pattern here, which is that somehow, even though you are writing a formula about a function which is a function just of a positive real variable, it's extremely useful to consider that function extended to the ideal classes. Okay? And to compose that function with the absolute value. That's a basic observation. Right. Okay, so now let us see how this extends. Okay, for future, for sort of bookkeeping, one should keep track of what is the additive constant. Okay, so it is this minus 1/2 of log p minus c over 2 plus, okay. So I mean, this eventually I will come back to that. Okay, but somehow if you want, we can see the pattern of what is going on. And the pattern is that, I mean, we have these local fields which are included in the ideal class group in a very particular manner. Okay, and we have also that they have covolume 1. And we also have this factor of 1 over 1 minus u, which is entering in the formula. Okay, so what I need to do now, you see, I mean, of course that's not yet very convincing because it's only for the Riemann zeta function, whereas when we consider these Adel class spaces, we have all Grossen characters. So now it is quite important that what I have explained here not only holds, if you want, for a function, for a test function, which is like this function here, which after all we have composed with the absolute value on the ideal classes. If you want, the test function that we have looked at so far is a function f of absolute value of u. Okay? But let me make, however, let me write the explicit formula and let me make a small change of variables. Very little. You see, okay, so I will make the following very simple change of variables. I will take the function h of u, which is equal to, I want h of u inverse to be equal to f of absolute of u times absolute of u to the 1/2. Okay? Let me make this change of variables. All right, so h is a function on ck. And in fact, I want to extend it. Sorry. Yes. Okay, we shall see what happens. Okay. Okay, so yes. So what do I want to do? I want to, yeah, no, that's okay. That's perfectly okay. Okay, so I want to take this function. I want first to compute its Fourier transform. So I want to compute h hat of a Grossen character and of a complex number z. Okay, for this function h. Okay, that might be a good place to stop. So I will erase, but what happens?
There's some book that came out by a woman like Clinton. Affair with. They didn't use the French words, so I don't know the.
Affair with whom? Mitterrand?
No. It's someone who's in charge of what they said would be an constitutional law.
Oh, Alexandre Dumas. Roland Dumas.
Yes, Dumas. That's who.
Oh, she wrote a book, the woman. Mon Dieu.
And now he will be removed. I mean,
It's temporarily removed.
Oh, that's terrible. She wrote a book.
Yes.
Wow.
Yeah.
She's really bad.
no, but he's not getting legends on it, like you said.
Oh, no, that's bad. That's bad. Oh, I would love to see some detail. I mean, is there a place in Columbus where one can find them all?
3 days later, it will be in the.
That's
library.
okay.
But I
It will be in the
look
library.
at Libération on the web.
Okay, so let me resume what I was doing. So what I was explaining was the following. I mean, as we shall see very shortly, when we are through sort of with this familiarization with the explicit formulas, when we compute the trace of the operator which is given by integral of h of u, v of u, sorry, u of u, u of u, d star u, acting on L2 of x. Okay, that is delta, yeah. Formally, because the computation is formal, of course. We shall get contributions from the various periodic orbits and so on, and we get a sum over places. So assuming transversality, namely assuming h of u is equal, h of 1 is equal to 0, so it will be a sum over places of integral of h of u inverse over 1 minus u d star u. Now what I wanted to explain is how this formula compares with the very explicit formulas. So, and here it is the integral over the local completion. Okay, star b. Okay. So I mean, so I wanted to explain some details of very explicit formulas and why similar expressions occur. Now what I had done very carefully the case of the Riemann zeta function. And in that case, what we did was to consider a function f of on r plus star, if you want, which was, say, compactly supported and smooth and so on. And what we showed was the following, was that we have the following identities that. So let me put an overall minus sign in front, so that instead of having minus psi of 0, I have psi of 0 plus psi of 1. Okay, and now I have minus because I put an overall minus in what I did before, minus the sum over the zeros of the multiplicity of the 0 times psi of rho. Okay, and that was equal to a sum. So assuming that the relation between f and psi was given by this formula, so it was given by a sum, but that sum was best expressed by considering all places and by extending the function f to a function on the ideal class group and integrating over the corresponding local field multiplicatively. We saw that for periodic numbers and for the infinite place of the following function. Remember what we had? We had f of absolute of u. We had u to the 1/2. And then we had d star u, where the normalization of our measure was as usual, namely of covolume 1. And we had this 1 over 1 minus u. Okay. So now what I was proposing to do at the very start of at the very end was the following. Let's make the change of variables that h of u inverse is equal to f of absolute of u times u1/2. Okay, so h is now a function on the ideal class group. Okay, so h is a function on ck, on the ideal class group. Now, let's compute the Fourier transform of that function, and remember that I had defined Fourier transform, well, at some point. Maybe I should write, no, let me just write it here. So the definition of Fourier transform was h hat of a Gaussian character and of a complex number was just given by the integral of h of u, chi of u, so I don't put any bar, okay, in other words, absolute of u to the z times d star u, where again our measure on the ideal class group is normalized by the previous rule. Now, if the function h only depends on absolute of u, which it does here, the integral, whenever the Gaussian character is non-trivial, will be 0. Okay, so I mean what we see immediately is that h hat of chi and z is equal to 0 if chi is different from 1. Okay, and moreover, if chi is equal to 1, then we should compute h hat of 1 and z, if you want. And that will be equal to, now you see h will only depend on absolute of u, chi will disappear. So everything will factor out through the module. And we know that by constructions, the image of the measure on r plus star is du over u, okay, by the normalization of the measure. So in fact, what we are dealing with is the following. I now have to put inverses, so it's integral over r plus star, if you want, of f of u inverse, because there is an inverse, okay, in the formula for u. Then I have u to the minus 1/2. Okay, no module because I am on r plus star. Okay, and then I have 1 over absolute value, where is it, of, sorry, f, what am I saying? H hat of 1z, no, what am I doing? Okay, so h hat of 1z, so this is here. Here I have put h of u. There is no chi of u, so it's simply u to the z, that's all. U to the z, d star u. Okay? Now, let me change variables from u to u inverse in this formula. Okay? So it's equal, in fact, so I put u inverse equals y. So in fact, it's equal to integral over r plus star of f of y, y to the 1/2 minus z, d star y. Okay, and that's exactly psi of z. Psi of z. Okay? So what you see by using this formula is that we can rewrite what I have written here in the following manner. I can replace everywhere the function psi by h hat. Okay? And in fact, I can sum now over all Gaussian characters here, because this function h hat of chi and z vanishes except at the identity Gaussian character. Okay? So we see that, let me see now. And now this will be replaced by h of u inverse. Okay? Okay? This expression here will be by construction h of u inverse. Okay, so what do we get? You see, we get that at least in this example, we have been able to write that the sum over v of integral over k star v of h of u inverse over 1 minus u v star u, okay, it's equal to h hat of 0. I don't write h hat of 1, 0, you know, I mean h hat of 0 plus h hat of 1 minus the sum over chi and rho, over all zeros, of n of chi rho, and then h hat of rho. Okay? So I suppose this is very clear. Fine. So now let me, so this was with the assumption that h of 1 is 0. Now you see what we want is we want to have this formula valid for any function h. Not only function h, which only depends upon the module. Okay? Namely, now we want to treat a function h so that h, if you want, of u inverse should now be equal to chi of u, where chi is a Grossen character, times f of u times u to the 1/2. Okay? So now we want to have arbitrary Grossen characters present. Right? Now, if you take such a function, what you will find out is that its Fourier transform is only non-vanishing at chi, because of the u inverse here, again. All right? So now what I want to do, I just want to show you what are the ingredients that makes this formula of André Weil valid in general. Why do I want to show these ingredients? Not that they are not in the literature, but that somehow, you know, if you take a formula from a paper, you cannot really trust it, because there could be a misprint, there could be a minus sign, and so on. And I mean, as I said, it's absolutely crucial that everything works on the nose. Okay? So that's what I want to explain. Moreover, there is another difficulty, which is that, you see, if you write a function, I mean, in the paper by André Weil, he was considering just the product of a function of u times a character. But you see, now it's no longer true that, imagine that I take a function which is of a finite sum of Grossen characters, chi alpha, you know, chi alpha of u, times f alpha of absolute of u times u 1/2. Of course, I mean, whether I use this formula or I use simply f alpha of u, it's the same, okay? Now, take a function which is like that, and call that h of u, and it's a finite sum. You see, I cannot, even if I have h of 1 is equal to 0, I cannot assume that each of the f alpha vanishes at 0, at 1, okay? So, I mean, it's no longer true that I can tell you what I was telling you, that I don't care for the finite values and so on. But at this stage, the only way I have to care about the finite values is relative, okay? Because what I have to show, you see, what I will know is that the sum of the coefficients f alpha of 1 is 0. So if I know about the differences, I am through. Okay? So at that level, which is still rough, I will only care about this. All right? And then at a final level, when we shall have the Zellberg trace formula, the analog of the Zellberg trace formula, we shall care about the absolute thing, which involves the Euler constant and log 2 pi and so on. Okay? Fine. So now what I have to do is to explain to you how you extend what we did just for the Riemann zeta function, which was sort of a simple, but I mean, which has this very nice way of writing it, how we extend it to L functions. So let me remind you of a few things. So the first thing is what is the function, I mean, what will be the functional equation? So I remind you that L of chi s, okay, was a product over unramified places, so V unramified, of the corresponding Euler factor, which is 1 minus the Grossen character at the place V at the prime here, and then multiplied by QV to the minus S inverse. And you don't count the ramified places, okay? They count for nothing. And then you also have to multiply it by a product for infinite places of certain factors, gamma factors, which I will denote by like this. So it will be GR of or R or C, according to whether the place is real or complex, of S plus SV, where SV is defined as follows. You see, you take the Grossen character and you look at it locally at the real or complex place. Now, at the real or complex place, as I explained to you, the Grossen character that I take, it's unitary. Okay, the non-unitary part comes just from the absolute value of the module to the Z. So it's unitary, so I can always write it as follows. So if V is real, say, first. So for V real, I can write chi V of U as being u to the minus epsilon times absolute of u to some power s sub v. Okay, and epsilon here is there only to account for the situation in which the Grossen character is ramified, in which situation it can depend on the sign of u. Okay, so when it depends on the sign, epsilon, so if there is a sign, then epsilon is equal to 1. If it's unramified, namely it doesn't depend on the sign, then epsilon is equal to 0. Okay? You see, the only way a Grossen character can be ramified at a real place is if it involves a sign of u. Okay? In that case, you put epsilon equals 1. Now, if you take a complex case, so if for v complex, okay, then you do the same thing, and you write this as u bar to the n, where n is positive, times absolute of u to the s sub v, again. And the absolute value, of course, is the complex absolute value, so there is a square in it. Okay? And here the n is positive, and you can always write it this way. You see, because, I mean, you can always absorb a positive n by u bar. Okay? So this is how you define the local factors at infinity. And now the functional equation takes the following form, that if you call that function psi of chi and s, okay, one has the following identity, that psi of chi and s is equal to psi of chi bar, the conjugate Grossen character, 1 minus s, multiplied by some constant here. So here there will be some constant a sub chi, which will be totally irrelevant for the logarithmic derivatives, okay? And here, then you have another term, however, which is the following. So you take a needle class, which is called the conductor of the Grossen character, and which is defined as follows. So this is a needle class, and this needle class is equal, it's a product, if you want, of the pi v's to the power nv, where this is over the ramified place. Okay? And nv is the order of ramification of the Grossen character at that place. So by the order of ramification, I mean that if I consider chi v, then chi v is equal to 1 on elements of the form 1 plus pi v to the nv times the maximal compact subring. Okay? I don't know if there is a plus or minus 1 here. Probably I need a plus 1. I don't know. We shall see that during the proof. Okay? Because I want to make the proof. You know? I don't want to give these things and tell you, okay, just look into a book because of the content that they have. All right, so
What is C?
C is a so-called differential idel.
Oh.
Okay? And for the time, it won't play a role because I am working with the condition that f of 1 is 0, that h of 1 is 0. But eventually, it will play a role. Okay, of course, when we want to prove Veil positivity, we cannot just ignore it. So we shall have to get it on the nose from the analog of the Zellweger-Trace formula. And this is what will happen. Okay? Now, how does it appear, this differential idel? Let me give you the definition. The definition is the following, is that you see, when you consider K included in the adels, it turns out that you can find that the adels are self-dual. Okay? The adels are their own dual group, Pontryagin dual group. And the pairing with the Pontryagin dual is just given by a basic character. So alpha is just a character from A over K to U1, and alpha is non-trivial. Okay? Now what you can prove is that any two such characters are related by multiplication by an element of K cross. So if you take another one and call it alpha prime, then alpha prime of x will be of the form alpha of Qx. Okay? For some Q belonging to K cross. Now, that was also a reason to take the quotient of adels by K cross. Let me explain why. Because if you then consider the Fourier transform with respect to alpha and the Fourier transform with respect to alpha prime, they will be related by multiplication by this element of K cross. So if you have passed to the quotient, the Fourier transform is now canonical. And that's what I did. Okay? Now, moreover, what you can show is that, you see, there is a standard local normalization of characters, additive characters, and then you can write alpha as the standard the product of the standard normalized character, okay, alpha of x, if you want, is equal to alpha 0, this is the standard normalized character, times Cx. And C is called the differential Liddell. That's the definition of the differential Liddell. Okay, so it's a Liddell class, and it's well defined. Fine. So I mean, this is what happens in the explicit form, in the functional equation. And now one can go, but let me explain the slight changes with respect to what we did before. So you shall again have local factors, of course. Okay. So in other words, I mean, there will be corresponding to this formula. Okay, there will be the local factors for finite places. So what will be the local rho, what I called before rho v of s? Remember, now we should decorate it with a chi. Okay? Remember that before, when we were dealing, we had local terms which were given by the logarithmic derivative of the local Euler factors. Okay? Now remember that they were always preceded by a minus sign. Okay? Because of this fact that we had 3 minus signs. And the local term, of course, it will be given by minus the sum from m equals 1 to infinity for the same reason as before. Okay? From sum from m equals 1 to infinity of what? Of chi v of pi v to the power m. Okay, I'm just applying the stupid rule. Okay? There will be the qv to the minus ms. Okay? Just as before. And there will be a log qv, an overall factor of log qv. Okay, so you grant me that. Okay? Now, you also grant me that I can rewrite this in a better way now, as I did before, because you can write this as the integral the integral over the local field, k star v, now, okay, which will account for the log qv as we saw from the normalization of the R measure. Okay? Of what? On elements x, so that norm of x is strictly less than 1. This is because I start from m equals 1, not from m equals 0. Okay? And then of what quantity? Well, you see, of chi v of x. I will write chi v of x. Okay? Then I will write, what shall I write then? I shall write absolute of x to the power s, and then b star x. Okay? Now, why is that true? It's true because you see, first of all, if chi v is unramified, then chi v of x only depends upon the absolute value of x. So I just have to integrate on each set of elements which have the same absolute value. That absolute value is qv to the minus m. Okay? And so I get exactly that sum with the right power of m and so on. Okay, I suppose this is clear. So if chi v is unramified, it is clear. If chi v is ramified, this integral is 0. But that's what you want because you don't have any contribution of the ramified factors in the Euler product. Okay, so that formula is always correct. Okay, and it's a formula for x less than 1. Now if we apply the Laplace transform as we have there, okay, what shall we get as a contribution from this? It's quite simple. What shall we get? That's not good. I don't want to use this very wet stuff, you know. Okay, let me use it now. Okay, so what do we get? We remember that we had two contributions. I mean, we had the contribution from the vertical line, the upgoing line, and the contribution from the downgoing line. So I mean, from the upgoing line, what do we get? Remember that this x to the s, okay, it will enter from the formula with the lambda to the z there, here, okay? So what it will give us is quite simple. It is just f of lambda. So it will give us, you see, and minus integral for over k star v, but for absolute of x strictly less than 1, of chi v of x, that will remain. And then we shall have f of absolute of x, x to the 1/2. Okay? I mean, this is clear. This is just applying this formula. And then d star x. Okay? But of course, I change nothing in this formula if I write over 1 minus x. Okay? Because we are where x is strictly less than 1. So this formula is not affected. Okay? Fine. Okay, so this is for the contribution of the vertical line. Okay. Now, if you look at the contribution of the downgoing vertical line, okay, what you will get? Well, you'll get chi v bar because of the functional equation. You see in the functional equation, right at the top here, there is a chi bar here. Okay, so there will be a chi bar, but precisely because you want to change x to x inverse, you will keep chi v, and because chi v is unitary. Okay, so exactly by the same argument as before, what you will get is minus the integral now over k star v, okay, but of modulus of x strictly bigger than 1, okay, of the same thing, chi v of x, not chi v bar, because I have done the change of variables x to x inverse. Okay, and you will have again f of absolute of x. Now, normally what you would get, it would be, okay, so you get x 1/2 over 1 minus x. And the reason is that this entity, absolute of x 1/2 over 1 minus x times d star x, is invariant under changing x to 1 over x. Okay? Because d star x is, and this quantity has a right homogeneity degree. Okay, that's why you can do it.
But the different and a chi don't contribute when you think these functional equations?
The different what?
If a chi don't enter the formula?
Oh no, this f of chi. Okay, of course they enter. Okay, and that's in fact the place where the contribution of André Weil is most striking. Because so let me write the formula. Okay, so what you're asking the right question. You see, after all, you look. I took this integral for x strictly less than 1, and here for x strictly bigger than 1. So I have ignored modulus of x equals 1. Okay, and now comes a very beautiful formula, which is really the key to this. Okay, this is the formula where for finite places. And the key formula is the following, is that, so let chi be a Grossen character, but local. Let chi v be a character. So chi v is now the local form of the Grossen character. Be a character of k star v. So k star v is a local field. Let me call it k. Okay? And it's non-Archimedean. Non-Archimedean. Okay, so now the key is the following. The key is that you have the following lemma, which I will prove, because it's really, as I said, I mean, it's not I mean, it's a fundamental fact, I think. And we shall use it, this lemma, I mean, much later. So the lemma is the following, is that the integral over the k star v and over the elements which satisfy that modulus of u is equal to 1 of the following, of 1 minus the Grossen character, chi v at u, divided by the absolute value of 1 minus u, times d star u. So d star u is, as always, a normalized R measure, so that the integral from 0 to lambda grows like log lambda. Okay, now this is equal to the degree of ramification, n sub v, times log of the local qv. Okay? And you see, I mean, this is called the Abraham distribution. Okay, so I mean, that's, I mean, the reason why it holds, this is the Abraham distribution. I mean, there is a distribution which is behind. Okay? So let's prove this. Now, first of all, you see, I mean, the signs are correct because 1 minus chi v of u, it's 1 minus a character, so the real part is always positive. Okay? Moreover, the numbers that you get is real, so it is positive. So the sign is correct. Okay? Now, how do you handle this? You see, we are in the case of a local field which is non-Archimedean. So what can we say? We can look at the invertible elements R star V of the field. This is certain group G0, okay, which is compact, totally disconnected group. Okay? Now this group contains a subgroup G1. Is there any problem? What? Sorry?
Independent of chi.
What is independent on chi?
Right-hand side.
Of course, NV is the degree of ramification. It depends on chi. You see, let me, well, in fact, we shall find out, let us find out what is NV from the proof, okay? I mean, it's much better, okay? So what we have the invertible elements, okay, in this, they form a group, which is, as I said, compact, totally disconnected, and so on. Now this group contains a subgroup, which is the elements of the form 1 plus the generator of the prime ideal multiplied by R, okay? This contains a subgroup G2, which is given by 1 plus pi v squared times R, and so on and so forth, okay? So there is this tower, if you want. The group is a projective limit, and we have this tower of subgroups, okay, G3 and so on and so forth. Now, any continuous function, in particular a character, will have to stop depending on what you are doing here. You see, the situation is like this. I mean, you have a group, okay, and it's projective limit, so each of these things is a group. Okay, I mean, these are coset spaces. So this is the situation. Okay? Okay, so we are looking at this thing. Now, so what do we know? We know that the index of G1 in G0 is the order of the multiplicative group of the residue field. Okay? So, I mean, it's equal to QV minus 1. All right? And the index of G2 in G1 is the order of the additive group, okay, of the residue field. So it's QV. Okay, so in fact, we know the indices which occur here very simply. And so we just have to go ahead and just look. Now, if we look, what shall we see? We shall see something very simple, which is that when a character on a group is non-trivial, it's well known that the integral of that character on the group is 0. Okay? So, and moreover, what we know is that the character will eventually be trivial when we go down this tower of groups. Right? So there will be, so now we have to compute this quantity. So what is it? You see, we can write this integral, okay, of where modulus of u is equal to 1. So in fact, it's an integral over r star v, if you want, okay? Of what? Of 1 minus, I'm always using the, oh, that's a pain. So over 1 minus u times d star u. Okay. So first of all, observe that the R measure, the total R measure of r star v is equal to log of qv. So this accounts for the overall factor of log of qv. Okay? Forgetting about that means that we can assume that the overall R measure of r star v now is equal to 1. Okay? So this is where we are on G0. Now, this is equal to the sum over n, okay, of what? Of the integral now over gn minus gn plus 1. Okay, this is not a quotient, this is a difference. All right, I am integrating on the difference. Okay? Of what? Of 1 minus KV of u. But now I can write the denominator, because when I am on gn and not on gn plus 1, okay, the modulus of 1 minus u, I know what it is. Okay? It is constant, and I have to be careful. It is equal to q to the minus qv to the minus nv. Okay? You see what I am saying here is that if I take an element u, which is in gn minus gn plus 1, the modulus of 1 minus u is constant and is equal to qv to the minus nv. That is clear. You see, for instance, take n equals 0. But not nv, I mean n. Nv didn't appear yet. But take n equals 0, for instance. You know that the module of an element of the form, which is in this group here, G0, but not in G1, its module is 1. Okay, and if you go in G1, the module will be Q inverse. Okay, and so on. Okay, so this is correct. And then the integral is this star u. Okay? Fine. Now, what do we know? As I said, we know that... right. Wait. What I claim is the following. I claim that the integral of KV of u on gn minus gn plus 1 is equal to 0 until I reach the place where it is 0, where KV is identically 1. Is that clear? You see, what I am saying is something very trivial, that if I if I take a character of a group, which is a finite group, which is non-trivial, then of course the sum of chi of g is equal to 0. Okay? But if that continues to hold for the next group, then I can take the difference and it will still be 0. Okay? So until I reach these points, all these terms evaporate. Okay? Until I reach the last. So what do I get? I get a nice formula, which is the following, which is that if I call beta n to be the integral over gn of d star u, and I don't care about the log qv, which is an overall factor, what do I know now? Okay, so somebody should dictate me what I obtain. You see, I am just writing that I can ignore these integrals until I reach the place where, which I will have to look at, of course, where chi is equal to 1. So in all the previous things, there is just a 1. There is this.
On the contrary, if n is big, then you will be congruent to 1 high power, and then it will be equal to 1, and 1 minus 1 will be 0.
Of course. But what I am saying, I am looking at the integral on the difference. I am saying that the integral on the difference, okay? I am saying that.
Ignore chi up to that point. At that point, you have to remember.
Yeah, let me not waste time. Let me just write you the formula because I'm no longer able to write it down without mistake. Let me just show you the formula.
Right, so at that point the integrals disappear entirely. But before that, you can just ignore the integral over the top.
Yeah. No, so in fact it's correct. No, it's exactly correct. You see, what you get is simply, well, okay, I mean, I was stupid. It is just the sum over n of what? Of, you see, I have this qv to the minus n denominator, so now it goes in numerator, so it's qv to the n, okay? Times what? Times beta n plus 1, sorry, beta n minus beta n plus 1.
Right.
Okay, where beta n is this integral. Okay, and what I claim is that the sum is not infinite, but it's from, let us say, 0 to m, where m is precisely nv. Okay? Okay? Now, let us compute this beta n minus, let me spell out this sum, and you will see that it's obvious. Okay, so the sum, it starts with what? So with n equals 0, so for I have what? Beta 0 minus beta 1. Okay?
nv minus 1 and then minus 1.
Sorry?
It goes up to nv minus 1.
Up to nv minus 1, but we shall see that. Okay? So beta 0 minus beta 1 plus qv times beta 1 minus beta 2, okay, plus qv square times beta 2 minus beta 3, and so on. Okay, but now let's compute the betas. So beta 0 is 1. Okay, I mean it's log qv if you want, but let's say it's 1. Okay. Now what do we know? We know that beta 1 is what did I say? That the order of this group in that one was qv minus 1. Okay, so beta 1 is equal to 1 over qv minus 1. Okay, and beta 2 is equal to 1 over qv times beta 1, and so on. But now you see that things arrange exactly well, because if I look at the factor of beta 1 here, it is qv minus 1. So in other words, this sum is beta 0, okay, plus qv minus 1 times beta 1, which is just fine. It's just 1, okay? And then what do I get? I get plus qv minus 1 times qv times beta 2. Okay, but this is 1. Okay? And so on and so forth. So what do you get? You get the sum of 1s with exactly the right number of them. So you are done. Okay? So I mean, that's obvious. I mean, perhaps you have to be careful, but I don't have the time for the last one. Okay? But, I mean, this is trivial. I mean, check it for n equals 1, and that's it. Okay? So you have this formula, and now what does it tell you? It tells you that if you plug it in, somehow the answer comes out right. Namely, now, you see, from the explicit formula for the finite places, so let us say, for instance, in positive characteristic, there is one term which I have forgotten. I have forgotten the term which involves the conductor. Namely, I forgot in the explicit formula to take in account the term which was f of chi, okay, to the absolute value to the power s minus 1/2. Okay? Namely, the absolute value of this thing. Now, if you take the logarithmic derivative, all right, you will get log of f of chi. Okay, and you cannot ignore this term, because this term depends on chi. I mean, any term which is constant just depending on the global field, you can ignore at this time. Okay, after we cannot be able to ignore it. Okay, but at this time we can ignore it. Now, here you cannot ignore this term. Okay, and it will contribute by how? Because it's a constant. Okay, it will contribute by this times f of 1. All right? Okay, because it's a constant. But now, you can write this as a sum, because it's a module of an ideal class. So, of course, it is the product of the modules of the local contributions. So you can write this as a sum over the places of the log of the absolute value of the local things. But what is this? This is log of QV times the ramification, by definition, because, I mean, up to a sign. At this level, I have to give up on the sign, okay? I mean, okay, so it is of this form. Now the beauty is that precisely because of this lemma, okay, this can be written as the sum over places now, so of course this is always involved, but now this means that whereas before we were only integrating either for absolute of x strictly smaller than 1 or for absolute of x strictly bigger than 1, now you can add the term which is the integral, okay, for absolute of x equal to 1, okay, and you see that this time you have no choice for the denominator. You see, otherwise you could have said, oh, why did you put 1 over 1 minus of u? I mean, why didn't you put just absolute of u? Because it's the same when u is smaller than 1 or bigger than 1. No, forget it. You have absolutely no choice. Now here you are obliged to write the function f of absolute of u. Of course, you can put absolute of u 1/2, okay? And now you put the character, chi of u, of course with a minus sign, because there was a minus sign here, so that's fine. Chi v of u, okay, divided by absolute of 1 minus u. This star u. Okay, so now you have to do the same thing, a little more work, to do the same thing to analyze ramification for the real and complex planes, okay? And it is very nice that it works. I mean, as I said, all this is unrevealed. I mean, it's a very nice thing that it works. So why does it work? I think I will just leave it as an exercise somehow, but it's worthwhile saying what happens. So let me do a very simple computation, because here I want to do all this computation. So let me do a very simple computation. Okay, so as we saw, the local factors at real and complex places were given by these functions gr of s plus s sub v. Okay, you have to remember that when you take a Grossen character, when you take fields which are not just rational numbers, Grossen characters can be extremely complicated at infinite places. Okay, namely, in fact, they are the duals of a solenoid, and they are much more than what you get from Galois theory. You see, I mean, there are more RKL functions than there are Artinel functions, precisely because of these Grossen characters at the infinite places. Okay, I mean, because, as I said in one lecture, you know, you don't have a Galois theory interpretation of the connected component of identity, and that can be huge. Okay, that can be quite wide. So you have to take them in account. And now the simplest situation, though, so this is for real place, and for complex place you have the same gr of s plus sv. Okay, so you see, as I said, we can be content in this first approximation with a relative thing. Namely, we don't care for what is the finite value, but we need to have a uniform definition for all. Okay, that's what we need. So that if h of 1 is equal to 0, the problem doesn't arise. So in fact, what we need to do, we shall need to compare rho r of S plus SB, okay, this is for the real place, to rho r of S. And if we can control this and express it nicely, we are in business. Exactly in the same way as here for fields of which were non-Archimedean, we were expressing the difference with a trivial character. Okay? So that's what you need to do. So what is this, in fact? What we would like to express it like. So you see, I mean, this function, I remind you, it was equal to up to constant. So I remind you that rho r is of S is up to constant. So there was the Euler constant and so on. But I mean, it was 1/2 of gamma prime of S over 2 over gamma of S over 2. Okay, up to constant. And up to constant also, so this is always up to constant, it was equal to the integral from 0 to 1 of y squared minus y to the s minus 1 over 1 minus y squared dy. Okay? We saw that. Now, if you look at this difference, we don't care about the constants. And what we would like to write it as is to show, you know, that this is equal to the integral over r, okay, for absolute of x strictly less than 1, okay, of what? Of one minus chi v of x times x to the chi v of x. So chi v of x is just the restriction here, divided by absolute of 1 minus x, d star x. Sorry, I need also x to the s, d star x. Okay, that's what we need to check. Okay, so it's very similar, if you want, to the handling of ramification for case of fields which are not Archimedean. Okay, so I mean, how do you handle this? It's a very trivial computation, but let me do it in the simplest case. So let's take chi v to be the non-trivial character, which is chi v of x is equal to the sine of x. Okay? Okay, in that case, we know that SV is equal to 1. So in fact, we should check that we get that rho r of s plus 1 minus rho r of s is equal to the integral over r for, as I said, I mean, it's r star, if you want, for this normalized R measure on r star, for absolute of x less than 1, and of 1 minus sine of x over 1 minus x absolute value, x to the s, d star x. So let us do this trivial type of check. Now you see, sine of x is equal to 1 when x is positive. So you only have half of the integral. But remember that you have a 1/2 normalization in the R measure, okay, in the multiplicative R measure. So in fact, this is on the nose equal to 1/2 of integral from 0 to 1 of, now, if I take x negative, I have a 2 here. But it will cancel the 1, which is here. So it's 2 over 2, okay? So what do you get? You get 1 over 1 minus 1 plus u now, okay? Because x is negative. And then you get u to the s and du over u, okay? Okay, and what we have to check is that it is the same thing as if I take this integral here, okay? Fine. And I take it for s plus 1 and I subtract what I get for s. Okay? Now, of course, for that I can ignore these terms. Okay? And so what do I get? I get integral from 0 to 1. I take the value for s plus 1 and I have to subtract the value for s. Okay? So it is clearly y to the s minus 1 because I have subtracted it. Okay? Minus y to the s. Okay? Divided by 1 minus y squared. Okay, times dy. All right? Now what is this? There is a 1 minus y which simplifies out. Okay? So this is obviously equal to integral from 0 to 1 of, so there is a 1 minus y which simplifies out. It remains a y to the s dy over y. Okay, and in denominator 1 plus y. So that's exactly the same thing as this. Okay? So, I mean, this is typical of what you do. I mean, okay, this is perfectly correct. All right, so, I mean, in fact, you would check the same thing, and I advise you to do it if you take a character which is slightly more complicated and still unramified. Namely, if you take the character which is given by absolute, which is sine of x times absolute of x to the I alpha, for instance. Okay, and you can still check it for this. Okay. Yes.
What you said the half in the last integral, you explained it better.
Sorry.
The bottom line you said the half.
Oh, this half mean? Oh, this is because of the normalization of the multiplicative R measure on R star, so that the integral for elements of absolute value smaller between 1 and absolute of lambda grow like log lambda. You see? Okay? Okay.
And what I'm doing the
Okay.
things.
Right. Okay, so what I did today was very down to earth, okay? I mean, I just went through these details. But you see, I mean, I think there is a lot of virtue in working very slowly through these details, because what we shall see later is that when we go to the finer stuff, where it's not relative, okay, where it's absolute, and you want to prove positivity of that distribution. So everything has to be perfect. I mean, you have to get all the right constants and so on. So when you do that, the fact that you know the proof to that degree of precision will be extremely important. Okay. In fact, what we shall see is that in this analog of the Zelberg trace formula, there will be some sort of cohomology when we take fields of positive characteristic, and it will be based on this Herbrand distribution. I mean, the fact that it works. Okay, very good. Oh, so the next class is Monday. Okay, Monday, next week.